yes.
I'll turn the audio on.
Or no, I mean, like I doused my copy of this version in coffee. It did not help much.
Is that like,
I was hoping it would work.
is that some sort of ritual? Yeah, so you,
Yeah. If you don't understand the paper,
pour coffee on it.
douse it in coffee, see if it gets better.
So
I've done that a few times.
this is an epic paper, honestly. So I think I should go over sort of the key things first, and then go through the paper and point out what's going on. So let me.
Epic in size?
Yeah, epic in size, scope. I mean, it really is a comprehensive model of the visual cortex and the thalamus, pulvinar thalamus. So let me point out some of the key things that I think we should take away from this paper. I think it's an interesting theory of how the thalamus fits into the cortical hierarchy.
By the way, it's a U, not an A. Just to,
Oh,
yeah. No, that's an A.
that's an A.
Yeah.
This is a U.
Yeah. I know you know that.
Thalamus. Okay. Did I spell that right?
Yeah.
No. Okay.
Yeah.
This is a big theoretical model of the whole visual cortex of pulvinar, which we'll get to in a moment. It presents this really comprehensive, broad hierarchical structure, all of the connections between all the different parts, and includes this idea of what and where. And this is sort of the fuzziest part for me, is the what and wheres. I'm not going to get deep into that because I don't understand quite yet how to do that. So we're going to get really far, I think, with just the pulvinar part. And we'll talk a bit about this, the hierarchy and the what, where, and the what times where. The big thing is they've created this structure and they've got out of it invariant representations of objects that are moving through this system's field of view, and they even have a model of saccades baked into it. So I'll talk a little of the details of that. And one of the things that I'll note throughout this, it's not highlighted, but there are lots and lots of non-hierarchical connections required for this to work. And so I'll talk a bit of that as well, because of the idea of the superficial layer and the deep layer sort of being in sync. Okay, so those are sort of the big ideas.
Are you and Florian presenting this, or is it just you?
I will happily include any input from Florian at any time.
I've read it, or try to read it as good as I can. It's a massive paper.
And it says Department of Psychology and Neuroscience. Are these neuroscientists or psychologists?
Cognitive scientist. O'Reilly has for a long time built computational models. Early on memory consolidation.
But detailed biological models?
Well, not biophysically detailed in the sense of spiking neurons, but biophysically detailed with respect to laminar pathways and
It's not hand-waving psychology. So.
Right.
Yeah, it's not hand waving. He's now at UC Davis actually. I've been thinking of visiting him.
So I'll go through some of the main highlights. The pulvinar thalamus, it very much talks about it as a projection screen, like we've heard about it before.
I've heard the word screen before.
Blackboard, perhaps. It's that sort of metaphor. So
yeah.
Well, so we'll get to the details of it, but essentially the idea is that there's deep layers and there's superficial layers. I'll go to the screen first. This. One of the main ideas is they've broken up the cortical system into superficial layers and deep layers, and they've simplified it based on that. So the model that I'm going to show you that they created doesn't have L5 and L6A and L6B and L2, 3, and L4. They've got a model of the superficial layers, and they've got a model of the deep layers, and they've got a model of the pulvinar.
So you've added that level.
I've added this stuff because I want to try and sync it to how we think about the cortical column and how it works. But I'm going to try and explain how their model works here, sort of on top of the layers and how we think of them. So the interesting thing I like to take about this is that the superficial layers, and let's start from the bottom. So this is a model of hierarchy, and this is one layer of the hierarchy. We've got the thalamus sort of on the bottom, which is a part of the L5 intrinsic bursting neurons that are coming from L5 of the layer beneath. And then this is one layer, and this is going up to another layer, and then
So they've already abstracted this to beyond V1. We're looking at V2.
Yeah. So that's mainly the model is of V2 and above.
Yeah.
They fake V1 a lot. So there's not a good model of V1.
Well, this could stand for V1. I mean,
but they didn't do it like that.
Okay.
So we'll get to that. That's one of the problems I think with the system. We got to figure out what that is. So one of the other main ideas, besides the idea of superficial layers and deep layers, and I didn't talk about this, but superficial layers are connected to input to the thalamus that projects to L4. So it's like input, and what they say this is a representation of current state of the organism slash environment. Depending on where it is in the cortex, it's current state, and then the deep layers are a predictive state of the organism slash environment. I know that's a generalization, but that's the model that they use to make this work.
I'm still a little confused about what this diagram is. This a model of V2 or some higher level?
That was a decent way of thinking of it. Yeah.
So then when you say thalamus there, you're talking about pulvinar.
Yeah. Let's think of Let's think of above V1 at least, because this is all.
Although in our world it doesn't really matter if you just say
Right. But I don't know if they can make this work with this being V1. I'm not sure.
Well, so far, the only thing you have to change right at the moment is to change the L5 intrinsically bursting to
sensory, whatever.
Yeah,
so this sensory, they don't do this.
Okay.
They don't do this. Would be sensory 2. So they don't feed sensory up the hierarchy. They've got V1 where they mock out, and V1's more like an encoder, some type of encoder, honestly. It's a Gabor filter sort of encoder system.
I don't know why they made that distinction. I mean, the copacetic ways is to consider them all the same, other than the fact you've got striated V1. You can pick that out of the picture at the moment.
The distinction is mostly because LGN is anatomically separate, and that has an effect on how you can think about it.
But the architecture is almost identical.
That's somewhat artificial.
Yeah.
I mean, people called they originally called this thing the pulvinar because it didn't get sensory input, but it got input from the cortex. But now the pulvinar we know is broken into multiple subregions that individually gets inputs from different regions. So it is equivalent. I don't know if they're physically right next to each other. I thought they were, but
they talk about the topological maps in the pulvinar of thalamus and how they relate.
Yeah, but that's true.
Yeah, but that's true of the pulvinar too.
That's true for
LGN.
LGN.
Everywhere, right?
Yeah, LGN. So the big thing was a long time ago. It was sort of to say, oh, pulvinar is not like LGN. Right. One gets input from the cortex. One gets input from the sensory inputs. But that was one of the things that Sherman and Guillory have really emphasized, that no, it's really just the same, and we just because we're getting input from the sensory input, that's just the first stage, but it's really doing the same thing. We can put that aside, but from our point of view,
because I don't know the
from our
answer
point
to
of
that
view,
question.
there is no, you shouldn't make a distinction.
You shouldn't, but this is very much a model of sort of V1 and above.
Yeah, so it should include V1, so I'm going to put in my mind that it's V1 too.
So that's one of the concerns, and that's something that needs to be resolved.
Yeah.
Okay.
Can I get a question?
Sure.
So, in this thing, is the LGN somewhere down below this?
Well, LGN is lateral geniculate
Geniculate
nucleus. That's part of thalamus, right?
Right, but it's not, I think, part of the pulvinar.
They don't really mention LGN. They talk about pulvinar.
Okay, so again,
LGN is the thalamic input to V1. Parts of pulvinar are the thalamic input to V2.
Imagine the thalamus has all these relay centers, a whole bunch of them.
Right.
And they're just lined up in there next to each other. For historical reasons, they grouped a whole bunch of them, called them pulvinar, and they called the other one all by itself LGN. But actually, there were just a bunch of them, and it's a nomenclature issue that they decided to group a bunch together and call them pulvinar for the reasons I just mentioned before, is that one gets input from the eyes and the others get input from the cortex, so they said they must be different. But now in the new interpretation, 25 years new, we say no, they're all the same. So it's just an unfortunate nomenclature issue. Pulvinar can be broken down into subregions. You can name each one, just like you can name LGN.
So for this, let's just call this thalamus and just leave it, because that's not all you need to know to understand the
Well,
model.
this is the region of the thalamus which projects to this particular cortex.
Yeah, exactly.
Yeah.
Exactly. And this is happening all over topology. There's a topology repeated across thalamus and across cortex.
And this same diagram applies to all the sensory modalities as far as we know. So this isn't even vision. This is what audition looks like and somatosensory looks like.
So one of the big theories here is that you've got current state of the organism, predicted state of the organism, and then an alpha cycle. And they put this together saying the alpha cycle is 100 milliseconds. And they break it up into quarters and say the first 75 milliseconds of this alpha cycle, and we're sort of jumping in, because there's no good place to jump in, right? This is a catch-22, you have to jump in somewhere. So assuming that we're in the alpha cycle, the minus phase is the predictions from the deep layers being projected to the thalamus. And then the plus phase is the new input coming up from the lower, from below and being compared to that prediction. And then there is a temporal difference mechanism that projects this error signal back to cortex, to the deep layers and the superficial layers so that they can do local learning. That's one of the biggest ideas, I think, in this paper.
Okay, you said they broke it up into quarters, but you're only talking about positive and negative phase.
Yeah, like 75% is the predictive phase where the cells are resolving to a prediction based on input, and they're going to predict what's coming, what's next going to be coming through.
Okay, so you're splitting into 3 quarters and 1 quarter. That's the division you're doing?
Yeah, so the plus phase would be the 1 quarter
Oh,
at
okay.
the end, and that's where the new input comes in, and there's a difference that can then be communicated through cortex from the thalamus. The thalamus isn't computing. The thalamus is like they call it a blackboard or a projection screen or whatever, because it's just a place for the cortex to project its deep predictions coming from the deep layers, compare them to, because it's predicting what it thinks is going to be coming next from the L5 intrinsic bursting neurons from below. So you think about this as a part of the hierarchy, but there's also sensory input too. So we're predicting not only what's coming from below, we're predicting sensory input here in these deep layers. So there's this temporal difference is happening every 100 milliseconds, and error is being propagated back through the cortex from the thalamus. The thalamus is just simply doing this very granular temporal difference error prediction, or error, propagation.
This is an old idea, right? This error propagation model.
I don't think it's new.
Well, it's old and new, right? Maybe it's helpful to back up a little bit why one would want to build a model that has like these temporal differences and or errors, right? In the first place, is to just simply say that lots and lots of good learning systems have been found in computer science using error backpropagation. Problem is that doesn't line up with biology, or at least not very neatly. Even though there's predictive coding models that have like error neurons, the direct evidence for these are like a little bit weak. So it would be very useful to have some kind of architecture that allows you to compute the differences between predictions and feed-forward input. One way to do that is to have a projection screen, a scratch board, a place where you can put out your prediction and have that be the same place that also feed forwards the actual ground truth. And the way that you are then capable of computing the difference, an error, right? Rather than having error neurons, you simply compute a temporal difference, and for that you need some kind of a rhythmic signal that switches between prediction
difference. What do you mean by temporal difference?
the temporal difference between what
I don't know what that
described
what
here as
does
the
it mean
minus
in the
phase.
temporal
State
difference?
of the thalamus.
I have an input coming in and I have a prediction what I'm expecting. In that case, there's no time. There's no temporal difference.
Right.
There's a difference
Now
between
there's a
prediction.
temporal difference.
But what does that mean? What does it mean? I have a temporal difference.
You want to explain?
So during the minus phase, the L6 cortical thalamic inputs are continuously active,
Yeah.
projecting whatever here, and this is resonant in some way as there's a switch to the plus phase as the new input comes. So there's a moment where I don't understand the exact capture.
So
but
it
they have
sounds
some
like the
mechanism
prediction is
involved.
represented in one part of the phase,
Yes.
and the actual signal is represented in another
So
part of
they're
the phase.
using this.
So
They're
the
using this.
difference you have to do.
It's not. It's funny the word you call it temporal difference. It's you're basically saying I'm trying to calculate the difference between these two, and I'm going to do it by assuming I'm going to have this sudden shift between the prediction and the actual. It's not really. It's just a difference, but I'm using time as a biological mechanism to calculate the difference.
Yeah, and this is a very confusing terminology because temporal difference error means something in machine
Yeah,
learning,
yeah.
and it
Machine
means something
learning.
completely different.
Yeah.
DeepMind did something right about temporal difference.
Well, no, reinforcement learning in general, it goes
Yeah,
back
it's
to
not
Barton and
temporal
Sutton
difference
in the
learning.
80s and 90s.
Right.
Yeah.
So that's not the same thing, not the same concept.
No, it's not the same. It's
But
very
you're using the
confusing.
difference in, across time that you get from the projection that you just got from the prediction versus what you now, couple milliseconds later received as the actual feed forward input.
So when you think about that, you have to think about another really important aspect of this model is that bidirectional connectivity all over the place is essential for this model to work out. We've got bidirectional connectivity between regions in the same layer, regions in different layers, from super to deep layers, from deep to super layers, And they had to do that. When I get to the models that they constructed, we'll see how they arranged all that when they created the visual hierarchy.
What are they trying to achieve?
I think it was invariant representations. At some point, somewhere, I think they were looking for them in the higher levels of the hierarchy, so that's where they found them. But they engineered this structure to try and
You said, well, first of all, you wrote that invariant representation of moving objects.
yes.
So does that mean it's only going to be invariant when the object is moving relative to my object?
No, meaning so
through field of view is
that's how they tested and learned.
or is this really invariant representations of through vision when I'm saccading? Both.
Yes.
So that says that I have to have a stable representation of the
Right.
object,
Right.
independent of where the eye is looking. So
Yes.
That's our we have mechanisms for that.
Right.
Where does that occur here?
So, okay, we're gonna have to go
Just point.
just
to-
point.
Well, you can go into it. I
We
don't
have to
know.
have a hierarchy to explain it. So I need to show you
So
the
this
hierarchy.
is just one piece of
Because
projects,
that's,
right?
you have to think about FEF and LIP and you know, I'll have to go to the hierarchy chart to show you.
Okay, but you realize when we go to a hierarchy, there won't be any additional information that you've shown here. I mean,
Mhm.
this shows a complete section, goes from one thalamus to the next
Right,
thalamus.
right. The important thing is
So-
the connectivity between the
Yeah,
different
but
regions.
so this is a key point I've been hammering for years here, that the hierarchy itself does not contain cells. It's a connectivity thing, and so the actual mechanisms to create invariants have to be in here. They can't be out. You can't magically point and say, well, the hierarchy is going to solve this.
Yeah.
So there literally has to be a place in the cortical column where there are changing inputs
Mhm.
and there are stable outputs. And the stable outputs have to be unique to the invariant object that's being observed through the changing inputs.
Right.
That has to exist here. It can't. You can say it's occurring in the thalamus, you can say in the deep layers, it's occurring in the superficial layers, but it doesn't occur someplace else.
Well, perhaps it occurs simultaneously throughout cortex, but one of the regions of the hierarchy resolves to the object and communicates it to the others.
Yeah, so that should be in here.
Yes.
So there has to
It
be
is.
some place that an invariant.
I believe it is.
Well, that means that if you're going to say L5 is projecting to the next region up here,
Right.
if that in this diagram, this would say that these cells have to be stable while these cells are changing, or these cells are changing, because that's what invariance means.
Right.
It means that I have these changing inputs, but I know underneath it there's a stable concept that's not going to change, and that's I don't think this is the right diagram for this, because also layer 2, 3 project to the next region.
They don't even account for that. Like they just ignore
Yeah.
that. They say it.
Okay. So anyway, so I'm just this is one of the key things to get at how the cortex create invariant representations,
Mhm.
and what it means to create an invariant representation. And boy, we've figured out that for decades. So so in this case, it has to occur here someplace. So we can say, oh, it's, and as people who've been around here for a while, Supersat will know. Every time we used to say, well, it'll be solved in the hierarchy. I say, bullshit. It's not solved in the hierarchy. It has to be solved here.
Right.
And you can do it over and over again in the hierarchy, but it doesn't magically appear in the hierarchy.
No, but you do have to construct a hierarchy at some point.
Well,
and
not
decide how.
necessarily. That's my
But
point.
if you're going to make something tied to sensory data, and you're going to create agency based on sensory data, you have to construct a hierarchy that is somehow resembles that sensory, somehow is tied to.
Well, our theory said that's not
set.
true, right?
I don't know if it's true or not, but
Well, our
it's
theories say it's not true. Our theories say, you can do this all in one region, and even that when you look at like a mouse, right? Its visual system is almost all V1.
So I totally agree with that.
So
I do think every region has the capacity to do the calculation that we need to do here.
Yeah.
But arranging them and with a certain connectivity emerges a system that does object recognition.
I disagree. I just think that's not right.
If you just have one, well,
I mean, you can. First of all, you should separate what you feel and what they're arguing from here.
sure.
It sounds like you're making your own argument here versus what they're arguing. So I'm not sure which of those.
I'm just trying to like link this with what we think. Like, what are the differences in?
Okay, in our world, everything has to be done in a cortical column. Everything. You can
Right.
put a whole bunch of them together and get more great stuff, but
Right.
there's no. It's not like, oh, this doesn't happen someplace. It only happens someplace else. It only happens in the hierarchy. It's not true.
Yeah.
So there's a limited amount of invariance you can get. Maybe the limited amount of object recognition you can get. but it has to occur in a quarter of a column. So this is why, I was jumping right ahead. Invariant representation, that's the key thing to ask about. And so the question is, where do you see in this model changing inputs and stable outputs? And,
Right, so I think that's one of the problems with this model, is you see the invariant representations at the top of the hierarchy.
well, it doesn't magically appear there.
No,
If you
they
do
force
this over
it.
and
They
over
force
again-
it. They do it intentionally.
So they're forcing and then doing like a backprop type of thing?
Yes, like
Ah.
an abstract, isn't it?
Well,
It's
the
a-
model
it's,
does a backprop not in an explicit sense,
Yes.
that an error would be fed back, but because the architecture is set up to have predictions in this minus phase,
Yeah.
and in a right, which lines up with like Sherman talking about the inhibitory effects of the layer 6 cells. Like,
Well,
it doesn't quite line up
Sherman
with what
has
Sherman says.
Sherman has said nothing. He has zero understanding what those back propagation projections are.
Anyway, the point I wanted to make is that you don't have an error signal per se, you don't have a concrete error signal, there's no error coding neurons here, but you have a prediction that is immediately followed by a feed-forward input, and that allows you to work, to use that difference, to harmonize the ideas of backprop with Hebbian learning.
What's actually, where's the errors, the difference actually being computed? If you don't have an error coding neuron.
Right, both the thalamus here, right, projects both to the superior and the inferior layers, and so both of those areas get access to that difference, to that temporal difference observation at the switch of the phase, right? When you go
Basically,
from
saying the
top
relay
down.
cells in the thalamus act like prediction errors.
Yeah.
At
and the
some
cortex
point.
learns from them.
Well, stop there for a moment. Just say, it basically saying at some points in time, the relay cells are encoding a prediction error. That's what this says, right?
Yes.
Okay, so they are at some points in time prediction neurons. At other
Yeah.
points in time, maybe not prediction neurons. That's how I'm interpreting what you said.
Right, and so the plasticity
Right.
is not in thalamus. The plasticity is still in cortex, both in the superficial layers, right, which learn to encode the current state, as well as the deep layer, which learn to build a prediction.
I have lots of thoughts about this, but I want you to, maybe if you want to keep going and sort of present the rest of the model.
Let me mention one thing about location. There's no location anywhere in this except for just one 2D topology of the input space. So as far as representations in here, these are all the superficial layers and deep layers and thalamus are all modeled with something called deep Liebra, which is at its core, it's a deep learning model, but it seems, and this is another paper that I didn't read, so there's a whole paper on this, but it seems to create a deep learning model with a bunch of models, each modeling hypercolumns, and then apply some type of localized learning between the hypercolumns. I didn't go into it. That's not the interesting part. I think of this. This is the interesting part. And there is no location inherent in the system.
When you're saying location, you're saying it's never representing locations.
Yes.
It's not like our reference
Yeah.
frames.
So
right?
just
There's
maybe
no
this
reference
is
frames.
maybe this is obvious to some people, or maybe it's just how my mind works. You could take this picture, swap in this layer 6, call those locations specific to objects. A location specific to an object is a predicted state.
Yes.
So my point is we can pretty easily take our model and put the pieces into this right now.
The way you draw exactly the same thing. When you say predicted state, well, that would be the grid cells sort of predicting what your next location is going to be. But we would go further.
Here they're predicting the next feed forward input through that.
But that's what a specific a location specific to object is that.
No.
No, I mean, it's not predicting the feed forward input coming from below.
This is predicting the feed forward input coming from
So the
below.
way our world would work,
It is.
the way our world would work would be the following.
Let's say grid cell.
You've got a predicted next
directly
location here.
predicting the sensory input, that would be happening in L4.
But it is a representation of that sensory input. There's a one-to-one
It's-
mapping.
there's a
Sorry, I'm
one-to-one
distracting now.
Yeah, there is a one-to-one mapping, but the bits that are on don't directly correspond.
That mapping has to be learned because
Yeah.
it's not, the location
But
to
you
the
could
sensory
classify the
input.
sensory input by hooking up a classifier to that grid cell representation.
Yes, absolutely.
So-
But I don't know if that's
I think
what, I don't know if
Sumitai's
that's, I
saying
think
is
it's
the
slightly
input is
different
not,
here.
this predicted location is not what you're expecting as an input.
That's right.
But it can be correlated or learned to associate with a particular input.
Yeah.
I guess that's true, yeah. Well, but in this model, it
Here,
is
there's a direct
compared.
correlation. The bits coming
I
down.
know, that is one of the
directly
problem here
correlate
is
with the
this idea of prediction like this cannot work.
Well, that's one of the things they say. They said Murray Sherman does not believe in this driver from L62.
Well, there are.
They're saying this has to drive it.
That's a different argument.
Okay.
All right, that's an argument. In fact, I don't even think they're saying it's a driver. They're saying it's a signal that's used to do a comparison.
Yeah.
And
It's stronger than what we thought. Or
anyway, it's a different thing. The point is, there's two reasons at least why this can't be a prediction for this. One we were just talking about, in our model, not in their model, in our model, if this was a location, like a grid cell type of thing, then the map between this and this has to be learned, because this on its own, the location on its own doesn't tell you what that's part of the definition of the object. What am I going to find at that location, at what orientation? So just knowing the location in our model, not their model, in our model, just knowing the location and the predicted new location is insufficient to predict the input. It has to be learned. You have to learn between these two.
Learned here.
Well, learn somewhere between this cell's activity and what it's predicting down here.
Mm-hmm.
This is not a prediction
So
of the
there is a loop here.
But you get that
right?
through the loop.
What do you mean the loop?
You
Well,
get that
there's thalacortical cells and corticophylanic cells.
The point is, this is the
It's not a
location,
loop like
and this
that.
is a sensory input,
No.
right?
It's not it is, the connections are there, but they go to the distal dendrites of the relay cells and to the TRN cells. They don't drive the cells. It's not a loop like that.
Yeah.
It's an anatomical loop, but it's not a functional loop in the way we think of point neuron
Right,
loops.
but it is a loop in this model.
I understand, but
Okay.
it does not correlate with the anatomy. That's what I'm saying.
Right.
Okay.
So
That's
the
fair
point is,
But that is how they explain it.
Marcus- That's a very different argument from the one Jeff is making.
Marcus made a very simple observation, or an important observation, which I would agree with, is that in our model, these are, you could think of these as location plus orientation prediction like this. This is where I am on the object. To associate that with a sensory input requires a learning. That in our model is here. That's between locations and grid cells and place cells. You associate with location with the sensory input. So if you have the sensory input, it drives the location. If you know the predicted location, it predicts the input. That's what this is all about. They're saying, no, that's occurring here. That this location is going to predict a sensory input down here. But for that to happen, it means that these connections between this and what's expected here has to be learned. That this is a very broad connection. There's 10 times as many cells projecting back here. They are not drivers. So you have to say, well, in our model, this can't be a sensory prediction. It's a location prediction. Therefore, there has to be learning. These synapses here would have to learn the mapping between the location and what the input is at that point in time. We're doing that up here, back and forth between here, which I think is more copacetic. They're proposing it down here. But the point is, if you just say this is a sensory prediction, and you can't even do that. Even if this was an encoding of the sensory input, and you send these cells down here, it still has to learn to associate that prediction with what actually happens, which it could do. But that means all these synapses down here have to be learned, and there are a lot of synapses on these predictions, so it could be. But you just can't. It just doesn't. You can't say I have some one population of neurons doesn't know what the other population of neurons represent. Therefore, to make a prediction between this population and this population has to be learned. It has to get from new synapses.
So you're essentially saying there's too much of a difference between this input and what's being generated here for them to be compared.
I'm just saying it just has to be learned.
It has to be learned, right?
Yeah,
Not
we
directly.
associate in our world. We have to learn this both ways. We have to when you have a new location, it has to learn to predict what the input was, and when you have an input, it has to learn to predict or drive what the location is. So these cells projecting here have to learn, and these cells projecting here have to learn, and they can learn because you have a location, you have an input, and you go, okay, I know those two, let's form those connections both ways.
Right.
The same thing would have to happen here.
Right.
You would have to form those connections that we assume between layer 6 and layer 4, you'd have to do between the thalamus and layer 6. It's all I'm pointing out. It's not to say that can't possibly be true.
And probably between.
Well, I don't know. You haven't
superficial
explained that one.
layers.
You haven't explained that one.
Well, they say that they put those connections in their model.
Which connections?
I think there's connections from Pulvinar to.
Oh, of course there is.
Yes.
Of course.
Yeah.
Those are the main ones. Those are the people talk about. They rarely even talk about these.
Yeah.
So, but that I don't. That's not part of learning them. In this case, that's what they're only doing here, saying that at some part of the phase you're sending up an error signal, and other parts of the phase I don't know what you're sending up. They didn't say that. What happens on the other alpha side? Other parts of that?
Well, just the prediction is being propagated down.
At one point.
At one point, the next one is
what? So
new input is.
Are they saying that the only thing that's propagated up is an error?
No, this signal is propagated up, and the error, I think, doesn't come with that signal. The whatever error signal is being communicated here and somehow from pulvinar to
well,
superficial
but you say
layers.
somehow the pulvinar, that's that arrow. That's the one we just saying. That's the one we just talked about. That arrow.
This one?
No, the one that goes in layer 4.
Oh,
I just
yeah.
said.
No, I didn't. I thought of that as for me. Those are. Yeah. That's right.
I just said that in their model that would be an error, and you say no. So
that's
No,
right.
it's
Sorry.
projecting,
Sorry. I was confused.
doing both phases, right?
So yes, the question is when it's not projecting the error, what is it projecting? Is it not being used?
It's projecting first the prediction and then the actual feed forward.
No, this is projecting the prediction.
No, the prediction is in the minus phase.
This go right here, prediction.
Exactly.
Yeah,
But
there's
what
a
is
phase-
this? What's this on? At this
That
point,
is projected, right?
that's the error between the prediction and the actual.
No, there's no error here. That's just the prediction. And you will
But this is the prediction.
right. So it's
Yeah.
it's a prediction, right?
One of the
It's-
concepts that they
so
throw
you
in
get
there is
the-
there's a phase shielding between the deep predictions coming from L6 and the input. So there's a separation between this that they insert
I
into
don't
this
know what
model.
that
So
means.
That's weird.
Oh,
yeah.
actually no. They
Let's
argue
go
very well
through
for
the
biophysical
I didn't even know what that meant. I still have a basic question. What does the thalamus to layer 4 represent?
Well,
That big connection, that's the one that everyone talks about. That is the driver to this column. What does it represent? I thought you were going to tell me at some parts of the phase it represents an error.
No. Again, there is no explicit representation of the error in this model.
So what is that projection to layer 4 represent?
That depends on when.
Okay, great. Give me the multiple ones.
Right. During the minus phase, right, this is the prediction. During the plus phase, it is the resolve feed forward input.
So you're saying that during the minus phase, this goes down here and immediately comes up to here, because this was the prediction, wasn't it? So you're saying at one point it goes whoop, and the next point it goes whoop.
Exactly.
But why go to here at all? Why just go from here to here?
Because you need a shared projection screen such that you can resolve across the different columns, across your
topologically in
network.
thalamus.
That you, right. For the
I don't understand what that means. What do you
Okay,
mean?
for the topology, right? So you have a highly topologically organized V1 and a reasonably topologically organized V2. And the point is that these areas the receptor fields of those areas don't see enough to be able to put that together with things like the motor saccade, right? So you cannot predict the response of a saccade in V1 or V2 because it's too low. You need an area that is higher for that. Because only at the higher
There's
area,
direct evidence against that, but
Our model says you can, and it explains how, but they wouldn't know that if you didn't have a location here. So let's keep going. So you're saying maybe this is a broader area of prediction, or it's just spreading the prediction somehow broader?
the minus phase is very long, right? It's 75 milliseconds, exactly in order to integrate all the available evidence.
But we're talking about topology now. Forget about the time. We're talking about topology. So the idea that you're going through the thalamus to sort of create the larger topology implies that somehow one of these projections is broader than the other one.
You want to pool all the different inputs during the minus phase to generate a stable prediction.
In L6, this is where that pooling is happening.
Well, no, through pulvinar, right? The pulvinar is a projection screen for all of this, right? Or thalamus, generic thalamus.
Is it possible that what you're saying is that they're thinking about the pulvinar not as separate little regions, but as this broader thing that's projecting to multiple regions?
Yes, they do.
Oh, that's
that's not
we're
correct.
proving wrong.
Well, you can argue,
Okay, that gets back to when I was answering Kevin's question about this, the idea that this pulvinar was somehow different than LGM because it's this bigger thing that covers all these different regions, but now we kind of know that's not right. So maybe that's
Yeah, you
sort of
probably
like-
want to show a couple more figures here.
Maybe this. Okay.
All right.
Okay, so
It's
I
answered
have
by the simple diagram here.
way down into this. So this is a little hard to explain. This is the macaque hierarchy, right? The standard one that we always see.
Which, by the way, they explicitly excluded thalamus from that hierarchy.
Yeah.
Right. Just so you- right.
Okay.
So we have they have
With
fixed
no
signals,
thalamus.
right?
Well, yeah, Sherman and Grill.
This is how they constructed their hierarchy. Okay, each one of these is a region, each one of these little groups, and they're broken up into S and D for superficial and deep layers. That's the granularity that they modeled.
By the way, you might not know that, but that is a very, very old idea. I'm not dismissing anything you're saying. I'm just saying it's not a new idea that these superficial and subgranular layers could be modeled as sort of two basic divisions.
Right.
That's a standard.
That's pretty fitting with the biology, I guess.
It's like saying we don't know what all these different cells are doing, so we'll just broadly break it into two groups.
Yeah.
It's clearly a large simplification.
So this is just the connectivity that they used to create their hierarchy that created their invariant representations. These are just the cortical connections.
Yeah.
Now I'm going to go down.
Can I kind of pull up there for a second? But there's a new idea I've never seen before here in this diagram, which is we talk about what pathways and where pathways, and they are introducing a third,
Yeah.
the what where.
Yeah.
What
Well,
times
it's not
where?
all that new. I mean, like in the Kennedy hierarchy already, they sorted out a third group of areas that are sort of like conjunctive and don't belong cleanly in one.
Yeah, I know, but I've never seen it explicitly spelled out like this.
Oh, yeah, right,
Maybe,
okay.
maybe it has been. I haven't seen it. So they're basically saying it's not like they're saying, oh, this diagram doesn't suggest like, oh, there's some areas we're not really certain about because they seem to be a bit of both. This is like, no, there's a what where hierarchy.
Straight up as the third, right?
Yeah. So that's a new idea to me, which I like. It's interesting to think about because
It's kind of core to what they built here. Like, I don't think it works without them doing this. I
well,
think
it
it's one
may
of
be
the
true.
reasons they did
All
it.
I'm pointing out is I had never seen that explicitly spelled out like that before. It's just an
I hadn't
interesting
either.
idea.
Yeah, I hadn't either.
And I think that's worth thinking about. Okay.
So this diagram is all cortical, and this shows how they connected up their different regions in their hierarchy. The dotted ones are superficial to deep and vice versa. The pulvinar comes in this diagram. So this is a little tricky. Can I make this bigger? Yeah. So we've got deep and pulvinar in V1, for example. Each pulvinar layer receives 5.1b driving inputs from the deep layers it's associated with. So this is a little bit backwards. The pulvinar is getting driving inputs from the deep layer right on top of it, which is actually a jump through,
you're
through
saying
the hierarchy.
V2,
or not the hierarchy.
You're saying V2 layer 5 intrinsically bursting cells are driving the pulvinar associated with V1.
No, I'm saying I would say that V2 pulvinar is being driven by layer 5 of V1.
Yeah, okay.
Which
Yeah.
is anatomically correct and well known and a
Yeah.
super strong pathway
Yeah.
and just the thalamocortical feed forward.
Yeah, and this V1 is really hand wavy. Like the way they did V1 is really hand wavy. I'll just say that. So these are the pulvinar to cortical. They all pulvinar cortical connections. I think they are.
But where's the pulp?
The
These
P.
all
The
the
P.
P's.
The P is, so
This
this is
just
pulvinar
shows-
and TEO, pulvinar and V4. So this is the whole hierarchy and sort of the connectivity between regions that they created to make this model work.
So can I just, again, I'm confused about something here.
Yeah.
In modern lingo, people wouldn't label that pulvinar. They would label it by the labeling of the sub-region of the pulvinar associated with that region.
Okay.
So in this case, it implies that all the P's are one thing. And maybe that's how they modeled it, right? But that's not the way we think it is.
I think they have different models for each pulvinar
My point is
region.
they're not saying, so if I look at the LIP region there,
Yeah.
is that the specific part of the pulvinar associated with LIP, or are they saying this is just pulvinar in general, and the pulvinar in general is getting input for all the different regions and is projecting back to all the different regions?
I think it's the specific model for the pulvinar associated with LIP.
So that's interesting that they would label it that way because, okay, fine.
Like it's important to deconflict two ideas that we've now talked about. So on the one hand, the pulvinar is shared. Maybe you can go to figure 2 that shows
That's
it.
the one.
So you can see that the pulvinar of like the V1P, bottom right corner, right, gets predictions, right, from lots of different areas.
Can I
Right. Even though
what is V1? How can the V1 have a pulvinar? What does that mean? Is that what?
that is your LGN.
LGN. Well, that's not pulvinar is never concluding LGN. So is that LGN?
They never call it LGN, and I don't think. They
So
just
they are
call it
using the word
pulvinar.
pulvinar, including LGN.
I guess so.
So that's all thalamus.
That's thalamus.
V1's really hand wavy.
V1, don't focus too much on V1. It doesn't help
Yeah.
much with understanding this model. The point is more that I wanted to point out that yes, all of these different areas here, these different blocks that you see there, right? You see these populations that end on P. These are the pulvinars, right? The thalamic higher order areas that correspond to that. So TEOP is the pulvinar that belongs to TO, right? Just like TOD are the deep layers of that area.
Yeah.
So this area does have separate sort of pieces of thalamus for different areas, but they can communicate to each other because they, as you can see, for example, in all those predictions converging onto V1P, right? There's a shared projection screen, right? The argument being that these are much wider than the feed-forward ones, like the driving ones are very specific, right? Whereas the layer 5 intrinsic bursting ones, right? The one that do the thalamocortical feed-forward, right? They're very specific, as opposed to the feedback ones, which are not all that specific. So that allows you to pool the prediction, right, through this shared screen.
Okay. And this might help with, it helps a little, but this is sort of how objects are shown. This is an object, that grayed out thing. This is a different object, you know what I mean? So that's how they define objects, some basic features arranged in a way. And they've got, 8 by 8, that's the field of view that's being modeled in V1. V1 is sort of a model of this, Gabor filter sort of model of it that's really too simple. But they allow the object to move through space, and they give it this 100, 200, 300, 400 milliseconds. They're trying to let the alpha cycle be able to resolve and
Are they
model that
associated? These
alpha
are all
cycle.
basically on a saccade.
Yes, so well there's motion and a saccade. So the object's moving through the space, and then there's a saccade plan that's somehow chosen and executed during the trial. So that's the invariance.
That's a little weird. You know, most vision occurs without movement through the field. Is basically a saccade. I mean, if I look at an image or a scene, most of the time it's not moving on its own. Most of the time I'm moving relative to it. So that would be saccadic or motion-driven changes. Occasionally, a bird could fly across my field of view. Even then, I'd have to not track it. I'd have to sort of, then maybe I'd track it and then I'd see something moving in my field of view. So it does occur, but
most of the time there's smooth movement, there's a smooth pursuit, there's no saccades.
Exactly. So it's interesting. This is a very important question as to how they're thinking about movement in vision. We would think about it as, let's start with one problem. One problem is I have a static scene or a static world and I'm moving through it. Which case there isn't movement across the retina, there are saccadic movements which changes the input to the retina. But that's why I was asking, what are they, can you go back to it, or you're trying to look at it?
No.
So the question is, it looked like they had both of them in there.
Yes, they have both of them in there, and
that's
in
not-
part,
it was figured.
and that's part of the challenge here, right? Because the model is supposed to learn invariant representations in the higher areas for the objects. Yet at the same time, you also have this one dedicated area, the FEF, the frontal eye field, right? Which we know does saccade plans and has representations for these things. But that is part of one of the streams.
Yeah,
which means you now have one area, exactly.
They're trying to do FEF.
Exactly. So you now have one area where you get that information for the saccadic information. And you have a different stream where that is not part of the picture, so you need to learn representations that are invariant to that. And that, in fact, leads to this whole idea that you can have multiple streams.
So I didn't follow that. I wish I followed better. But one of the constraints I put on our work was that I have to be able to understand invariant representations in static environments. So as I move my eye over something, I need to be able to build a representation of that thing. I need, and the representation of the thing I'm looking at is stable while my eye is moving, and that that tells you that the brain must be predicting what the input's going to be, if it's learning object, all this kind of stuff. So but you could break the problem apart and say, yeah, there's a static image recognition problem, and I mean static doesn't mean that nothing's moving. It means your eyes are moving, but the object, the world is not moving. Like if I walk around this building, as long as there's nothing moving on its own, the inputs are constantly changing, but the underlying structure is the same. You have to solve that problem, and you have to be able to understand vision in that problem. Then separately, you have to be able to say, hey, but what if it was something moving, like a bird flying? How do I see that, or someone dancing, or something like that? But you have to be able to do both of those. So the question is, does this model deal with the first problem, which is, hey, I have a world in which I'm moving. The world itself is not moving. So the only time the inputs change is because I'm moving my eyes or moving my body. But there's nothing ever moving across the retina. It's not like there's something flying across my screen. It's only I move to make things happen. That picture was confusing to me, this one here, because
Model learns both.
It does both,
definitely
which
does
I think
both.
you have to be able to explain. The more important one to actually explain how it is I build a model of the world when the world isn't moving. I'm moving.
without
So
What's wrong with the model that does both?
They kind of present
there's nothing
this.
wrong with both, but I have to explain how one works. I
Right.
can't rely on.
And they do that because they have dedicated representations for the saccade plan in this area that they call FEF, right? Frontal IVF.
So that was my question. My question is, does their model rely on this movement across the retina? Or can
No.
I say,
I think they added it to make it more realistic. They try and make it more
challenge the
realistic.
model.
Yeah.
okay, but I first have to be able to explain how I get invariant representations without it. I mean, I have to.
I think they could have made a paper without adding movement.
Yeah,
honestly.
I don't think it would have been a problem for the model.
Okay.
Right.
Okay. Well, we're getting really into the meat of it, so let me go in and find some key points that I want to make sure I didn't miss.
Just go through the
I got
highlighted
about
stuff, Matt.
15 minutes.
Yeah, just go through the highlighted stuff.
It's the yellow stuff that's the most important, so let me share my screen here. Okay, so one of the things about what and where that I haven't figured out yet is for this model to resolve the invariant representations, it does it in a top-down fashion. I've got some notes on this. There we go, top-down learning. So apparently what they try and do, because you saw how they had it separated into what, where, and what times where, they start the object recognition process, however, whatever that means, in the higher levels, and then the
Higher regions.
Higher regions, sorry,
Higher-
yes, higher regions, and those inform the regions in the what area, which provide details that resolve the object. I don't have a good understanding of this, honestly. This is the hardest part for me to get, and there's a lot of detail about how they set up all these pathways. There's pages of it, you know, like how did they set up all the connections and build all the pathways and everything, and that I don't quite understand. So if I were to continue investigating this, I would look into the what, where stuff. This is another decent graphic to look at with some detail.
Yeah, this might explain some of the error stuff that we talked about.
Yeah, although it's super hard to get a sense of this.
But I think I get it.
Maybe you can explain it.
I think I can explain it.
Okay.
All right. Let me just double check that I also have the help of my own notes on top of
But
this.
just to note, this is a cortical column, and this is the same cortical column with its link to pulvinar 100 milliseconds later, and this is 100 milliseconds later. And there is a hierarchical connection in here somewhere.
And this one's definitely dealing with movement through the field.
Yeah,
So.
it's dealing with movement through the field.
Right. So you see the quote unquote normal thalamocortical feed forward from V1, as sort of like the bottom left, which is essentially just your input, right? So you have an object, and this is actually one of the tasks that they did. They didn't just like moving and tracking objects and building invariant representation and predicting what you're going to see based on saccades. They also did things with like partially occluded objects. Right, and so what you are seeing here is you see that pulvinar level, the pulvinar thalamocortic relay cell, the TRC level, and you see that there's two boxes left and right. These predict these are the two states of the pulvinar representation during the minus phase and the plus phase. During the plus phase, it's driven by the feed forward input, which gets relayed by the pulvinar into both the superior and the deep layer just above it.
This bit, yeah.
this bit,
Yeah.
right? So the red arrows are all the feed forward, which happens at the end of the alpha cycle, versus the rest of it, right? Before that, the pulvinar is in a different state, which is in this predictive state, which is driven by the V2 deep layers. It's a top-down prediction, right? These layer 6 cells, right, that are projecting back into V2, which then sort of that's the state in the so-called minus phase, and this one also projects upwards in the blue ones, which are essentially the predictions fed up both in the superior and into the deep layer. Of course, as noted there, the deep layer is in the previous time context, so you should always think of it as prediction first, and then comes the actual information. And so you now don't have an error signal per se, but you have an implicit representation of the error if you have access to the difference between these two different inputs that you're getting from pulvinar. First, you're getting one that is a prediction, and then followed by that, once that is stable, right, you get the actual information, which gives you a temporal difference, which can drive a learning algorithm. And so you can then step through time, this entire thing. So stepping from the left column that I've talked about now to the one further to the right, and sort of propagate this whole thing through time, right? So these are 100 millisecond increments because these are all these alpha cycle. And every alpha cycle always has a predictive phase and an actual update phase, right? And you can learn from the temporal differences that you are seeing.
Can I stop here for a second?
Mm-hmm.
So this answers some of the questions I had earlier, which was that here we see that both the deep layers and superficial layers are getting inputs from the thalamus in both sets of time here. So both are getting the actual and both are getting the prediction, right? Because they both get blue and they both get red. Now there's a question is why you have two that are getting both those. Is it the idea here that the deep ones are sort of representing T minus 1 or something like that? I mean, in some sense, the deep layers and the superficial layers can both calculate the temporal difference because they both have it. So I'm looking at it, it's not really clear why would you want both to get that?
Why not do it here?
Well, it is going to be there. It's doing both.
Could be here, could be there.
It seems like they're both getting it, right?
Yeah, they could. They could both.
Right. But this has to do with the fact you see that by following the pictures that the superior layers and the superficial and the deep layers. I'm so used to saying super granular and infragranular. Layers are temporally not in the same time, right? The deep layers are one time step back.
Yeah.
Right? In part because
But they both get both, right? In this case,
yes.
The deep layers are going to get the prediction and they're going to get the actual. And so with the super layers are going to get the prediction and the actual. So there really isn't a difference there. Why is there a difference?
They should both be learning from the error signal, it seems.
Are they saying the error is only calculated in the superficial layers?
No, I think it's because of the context update that you get there, right? So this path there.
No, but I'm just pointing out right now on the first column on the left, both are getting the blue arrows, both are getting the red arrows. So they're getting the same input in that regard.
Right.
What is the difference in how they're calculating it? They've only labeled error on the upper arrows. I don't know if that is
It's
important.
true on the lower one too. So, these are the same.
So
same
now
numbers.
I have these two upper and lower cells that are both getting the actual and both getting the prediction,
Right.
both calculating the error.
I understand.
What's the
The
point of
difference
that?
becomes obvious when you look at the next time step. Because you will see that the deeper layers have the context update, right? So they share what was true from the previous time step. That's why the deeper layers are always one time step behind. And
So that connection is not in that diagram, I think.
no, it's not in this diagram. No.
Which
By the way,
one?
that connection is really, it's not, I don't even know if that connection exists, does it? Between the superficial layers direct to layer 5 intrinsically bursting? I didn't think that was true. Is that true?
Yeah, well, there's 3 hierarchical output which comes up with alpha.
It goes to the thalamus, but that's showing it direct there. That's
true.
showing it direct to to the,
Oh,
to the
that's-
deep layers.
And the 2-3 output does not come in as the intrinsic.
I don't
reversing.
understand. The layer
No,
2-3 to layer 5 is one of the most dominant pathways.
No, layer 2-3 to layer 2-3-4 is dominant. There was also, but it goes to layer 5, but I don't think it's the intrinsically bursting one. I thought it was the other layer 5 cells.
Mhm.
I could be wrong about that, but
I mean, that's a detailed anatomical question. One
well,
can
it's
answer.
important to this diagram. This,
Right.
this is the key to this whole thing working here, right? That black arrow that says 5-1B, 5IB context update.
Yeah. Okay, hold on.
I don't know.
I think they talk about.
Maybe I'm wrong about that. Maybe that's the anatomy. I didn't think that anatomy was there.
Okay.
I could be wrong about that.
During each alpha cycle, the V2 deep layer uses the prior 100 milliseconds of context information to generate a prediction or expectation over the pulvinar units that will come in next via the 1.5B strong driver inputs from B1. That's what we're talking here. But so it's a context update here. The system's predictive, they call it a predictive autoencoder a lot, because it's learning to generate a representation of the V1 inputs as
If you go in the
Coded
middle
via-
of that paragraph where they talk about the 5.1B bursting.
5-1B bursting
There it
V2
is.
drives an update of the local temporal context information in V2, which is used, yeah, but that's not talking about that arrow. Well, no, the next thing is this, these same 5-1B cells, 5IB cells,
Yeah.
drive a plus phase and higher area TRCs as well. Yes, TRCs is,
So it's going through
that's the thalamus.
thalamus. This is through thalamus.
Okay, they're not showing that there. It's
Right.
funny because this whole thing is about the thalamus, but they're not showing that picture, that driver going to the thalamus.
That's true. That's weird, huh?
Yeah, even though
They
this,
just
It's black. Maybe that's
yeah, but
how
that
they
means-
signal that.
But it's funny because we have the picture of the thalamus. The whole point is showing these connections to the thalamus. And it even says, drive a plus phase and higher area TRCs, which is the thalamus. So I'm particularly, I guess, particularly because
Well, they got the pulvinar layer down there.
yeah, but they're not showing the black arrow going through that.
how,
Yeah,
but
yeah.
this doesn't make sense. If this is the same cortical column, how is it getting an update from itself through the thalamus? It's the same cortical column. I mean, it's the same structure. But
Yeah. Well, I don't know. It's not clear why they drew that black arrow like that.
yeah,
They'd love to find the exact paragraph where they argue for this projection.
Well, layer. Okay.
Do the L2 3
Okay,
cells.
all right. I'm sorry. I was confused. I made a mistake here. I remember we talked about that. If this is the same column, then we're just saying that the superficial layer cells project to layer 5.
Yes.
Not, okay.
Yes, that's it. That's it. This
Okay.
is not a hierarchical thing. It's just superficial
Although
cells
down
project to
here
layer
they say
5.
the layer 5 IB bursting in V2 drives an update of the local temporal context in V2, which is, no, the next one. These same L5 IB cells plus a phase and higher, it's from the same kind of local, but okay.
I think that's where they're talking about the hierarchy from V2 deep up to the next one. Those are.
But that black arrow then is not a hierarchy. That's
You're
just-
right, this black arrow can't be
that-
hierarchy.
That's
No, this is not hierarchy. This is just in
Yeah.
time. This is just
Okay.
the next time step.
Yeah.
I'm sorry.
That's the confusing
I got
bit. This is
confused
not
about
a
this.
hierarchical
Yeah.
connection. This is just
Right.
L2, 3 to L5 in the same cortical column.
Yeah.
Okay.
It's funny because on the left, each one of these 3 blocks, there is 2 cycles of the alpha cycle, I guess they're saying.
Right.
Yeah.
But so there's 2 points, they're representing 2 points in time, but then there's also moving forward in time to the next one, which is the next block.
Yeah.
So,
It's hard to see this properly, right?
no, I think I get it better now.
It is. There's.
So temporally, I understand, between the prediction and the actual plus and minus. So this context update, do they have any temporal phase associated with that, or does that arrive on the plus side or the minus side of the alpha cycle?
No, I mean, it's just the end of the alpha cycle, right? You essentially just get, I mean, like in this diagram, right? It looks just like the deep layer gets a copy of the V2, right? To hold on to make a prediction, right, for what's coming next.
Okay, so you're saying it's a retained signal that's available on the next alpha cycle.
Well, no, it's being used immediately for generating the next prediction. This whole thing is
Yeah.
continuous.
There's like a pumping going on here through the cycle. Like
Right.
you look at the darker ones in the top left and then the lighter ones in the bottom right. That's the different parts of the cycle. The plus phase and the minus phase is the prediction, and one is primed by the other.
Okay.
When we're ready to wrap this up, I want to see if I can make a very broad summary of this, see if I got it right.
I think our time is up, so I think
May I take an attempt at this?
Well, yes, let's do it.
Where's the black? So I'm going to try to make the highest level description of this I can. We have this concept that you've got a bunch of cortical regions that are somehow connected like this. This is an old idea. And one way to think about this is that you have invariant representations up here at the top of the hierarchy. I wrote about this in On Intelligence. I think it's wrong, but I'll tell you in a second. And then I think what you're saying is, well, how could I get this whole system to work? If I basically impose stability here, invariant representation, then what kind of system would work like this, making everything work out right? I think that's what you're trying to describe.
Yeah.
Right? That's the general way of thinking about it. That's the way I thought about it. That's the way deep learning networks work. Right. I no longer think that's true. And you have something like this. In our world, when you have grid cells in here, or location and reference frames, then each region on its own can create invariant representations. It doesn't need a top-down signal telling it that. It's on its own, the whole mechanism, and it completely relies on having that location signal. So now with the location signal, I can integrate inputs over space, not just over time.
Right.
And so I can get an invariant representation here, and I can pass that invariant representation up to this guy, which can actually build invariant representations of invariant representation, something along those lines.
Yeah.
But I don't need to impose this down on the top, but I don't need to impose it anywhere.
Right.
I don't have to enforce stability. It comes out naturally in the learning algorithm that I get invariant representations. Every cortical region does that. So now that basically says, oh, these guys are all building invariant representations. Now I can ask how I can rearrange them in different ways. But this is the idea that this one, no, you're going to start with some invariant representation in some high-level region, and you'll propagate down some sort of signals that help you learn that. That is the basic divide where they're proposing a mechanism for doing this, and I don't believe that's happening anymore. I believe this is happening. And
So I think the only reason they're proposing this is because the models that they're using perhaps don't have the things that we're talking about.
No, this is everybody in the world thinks this. I used to think it
know,
too. There's nothing wrong. It's not stupid. It's a good idea.
Right.
We used to believe it too.
But I think this is the right model, and I don't think this is necessarily evidence against it. There's some problems with this model.
No. I'm just trying to summarize all of this in my mind. If you start with the assumption that invariance is going to be imposed, or it's going to only exist at one point in the hierarchy, then the hierarchy is justified to get you to that invariant representation.
Right.
That's how everybody thinks about it, going back
Right.
to Hubel and Wiesel. It's just like that's the way it is.
But if you notice in this one, there are more lateral connections than there are hierarchical connections. Those seem to be more important for the system to resolve.
Maybe,
This is
but
not a rocket
I'm trying to get rid of all that detail and come up with the highest level, simple description of what's going on. They've got maybe a very clever way of doing this.
Mm-hmm.
Maybe that's the cleverest way you can do this. I'm just pointing out our theories are no longer doing that. Our theories are doing this, and that doesn't. I'm not going to say which is right or wrong. I'm pretty sure this is right, but we can just leave that open for now. Just say that's the difference here. And so as we look at all this, and we're struggling with trying to understand that all these details are under this idea that you're trying to impose stability at the top. I think that's what you said, and then propagate and figure out how these guys learn what to do by passing these signals around. Where I now no longer believe that's the case. I think every region is capable of complete invariant representations of some limited amount.
Yeah.
And that's the fundamental distinction between our world and their world.
Let me just note that I don't know how they're imposing stability at the top. I don't understand that yet.
No, they actually don't. I don't think this is an accurate representation
Well,
of
you
what they
said
were
that. I
trying
only
to
said
do.
it because you said it.
I'm probably wrong. In invariant representations, they say they had to form their models in that they would only emerge at the top of the hierarchy. They used a strategy to do that. So they built an architecture where invariant representations emerged at the top.
Okay, so you don't have to impose it. The point is the invariant representation is only at the top. That's the key item.
That is no, it's not the key to this paper.
No, it's a key difference between what we used to think and what we now think.
Yes.
right? That's a huge, huge difference.
It is.
Everybody in the world thinks this, including us, that we used to think this. So, I'm not being critical about people then.
Right.
It's just that we now discovered there's something else going on. We've deduced that there's these grid cells, these location signals, and now all of a sudden, holy crap, it's a completely different idea of what's going on in each region. It's not building up to an invariant representation. It's invariant representations everywhere. And they can vary in context, they can vary in space and time and whatever, it doesn't matter, but they're completely, and I don't need to have a hierarchy.
I don't think that is what they're talking about.
Why not?
I honestly don't think that's the.
Okay,
the
I'm just
angle of
saying
it.
what you
Yeah.
said. You're saying that they're not
So-
applying invariant representation only at the top.
No, the whole thing is unsupervised. There's no
Okay,
supervised.
I'm taking that out. The question is, does
Okay.
invariant representation only occur at the top?
Oh, well, that depends on how you measure invariant representations, but that's not the point of the model. The point of the model is to try to explain a lot of other things. Like,
But underlying the model, is that an assumption or not? I'm just reacting when I'm saying, is it an assumption that the invariant
I don't know, I think it's an emerging outcome of the model. That,
They were
that
trying
you
to get
get
any invariant.
invariant representations in the part of the stream that does not get the saccadic input plans and whatnot, so it doesn't do the where, it does the what mapping. Yes, you get invariant object representations higher up the hierarchy.
Okay.
True.
So forget it. Maybe they don't impose it here. The question is that your essential assumption? I'm asking that you have this hierarchy of stuff, and then at the top you have invariant representations.
That's what they saw. I don't know that was I mean, they built an architecture, and that's what they saw occur. They tried to mock the visual cortex, and but the biggest problem to this is that V1 is so inaccurately portrayed. Like there's
Maybe that's a problem. I think, to me, I'm trying, and I'm guessing it's a question. I'm not saying I know things. I'm just hearing what I'm saying. I'm trying to understand. The world has always assumed that a local column in V1 or V2 or V4 can only know about what its inputs are. Therefore, to form an invariant representation of the entire input space, you would have to have this converging hierarchy. That is the assumption. I no longer believe that's true. I'm certain it's not true. And so I guess I'm not even saying that was what they were trying to achieve, but it is under that class. It sounds like, I'm asking, it sounds like, if I'm wrong, tell me, that is still sort of the working assumption underlying this stuff. And you could say V1 is ignored because that's part of the problem too, because I remember there are people who think that V1 doesn't learn anything.
I think it is a working assumption that they're going through when they built their hierarchy, but what also is really appealing about this is they had to model all of these lateral connections to get anything to work at all.
Yeah, but you understand if you're basically...
Where are the lateral connections in here? I didn't quite
They're like everywhere.
Everywhere.
There's deep, there's super superficial connections, super deep connections, deep super connections.
But that's not lateral.
You're saying lateral
Well,
between...
non-hierarchical.
Well, that's very different from lateral.
Okay, let me say non-hierarchical.
Okay.
There's many more. They had to add a ton of non-hierarchical connections just for this bidirectional connectivity. That's what they're saying. They did that for bidirectional connectivity, so everything can resolve to some attractor dynamics.
Well, but
through the
bidirectional
phases.
connectivity within a column? Or
Yes,
because-
yeah.
Well, that's not lateral.
That's not lateral.
That's just
yeah,
bidirectional
yeah,
connectivity.
Between cortical columns,
Well,
There's-
between cortical columns would be lateral.
But within a cortical column, it would not be lateral.
this is between columns, sorry. This is, I don't know that they talk much about inter column connectivity. They talk, all of this I think is about between cortical columns.
You were trying to say intra-column.
Inter, sorry.
right there,
Cortical columns at the
this
same
layer-
level or different levels?
Both.
All these arrows you drew here,
All of these are not
these are
lateral
all
connections.
within a column.
These are all within a column except this.
Yeah.
Well, but that's still not,
And
that's still
those
not.
are not lateral connections either.
Right, I didn't draw any of those I didn't draw any of the column to column non-hierarchical connections, but there's a
You
ton
showed
in
the
the model.
diagram with some of them.
I did show a diagram, let me go.
I think that the main point of this model is really something different. It's really about
This is
building a
the-
model that can explain things
But
like the
those don't show lateral
alpha.
connections either.
I'm sorry, say it again? You think it's about explaining things like the alpha?
I don't think this model is about a hierarchy and about invariant representations. I understand that is the lens you have on.
No, not true, I'm just reacting to what Matt said.
Right, and
Okay.
I
Sorry,
understand.
Matt, I'm not being critical, I'm just saying that's what I'm
Right.
reacting to.
I'm still trying to figure out what it's all about.
Okay.
Right.
So you have one interpretation, exploring what you're interpreting.
At least to me, right, this model is about rather different things of of rather dominant, well-known findings that are inadequately explained by existing cognitive or computational neuroscience
What were the
models,
key ones?
which are things like the algorithmic theory of attention, things like predictive remapping, which are not explained by any of these models or the HTM model for that matter.
Predictive remapping does.
Yeah. So the idea that when a saccade is about to happen, so you have a motor plan,
Yeah.
right, about to move the saccade over there.
Yeah.
There's all this evidence that cells in the can
Anticipate.
remapping,
Yeah.
anticipate are remapping their receptor fields already in anticipation of
Yes.
the saccade,
Yeah.
right? And for that, you need a model that actually needs to have some kind of representation for that, like saccadic plan. So you need something like a frontal eye field. And if you do that, and you separate that from sort of other parts of the model that don't have that, then you automatically get what you might call visual streams, because you now have one area that has all this information and can learn to map these inputs corresponding to the saccades and predict what the saccades are going to do before the feed-forward input comes to correct it, right? Whereas you have another part that instead builds what representations are a lot more object specific representations, and at least to me, I've not seen any model that sort of uses one unified mechanisms to explain not just algorithmic theory of attention, but also this predictive remapping. A couple of other
The
interesting
great thing does predictive remapping. Totally. I mean, it basically uses the locations to do that. It basically, if I know what object I'm observing, then I can predict my new location on the object, and I can predict
Based on movement, yeah.
based on movement.
No, hold on, but that comes feed forward. I'm talking.
But why would I want it to come back? Why do I don't even want it to come back. I want to be able to do it all in one cortical column. The assumption has always been that the remapping can't occur in V1 and V2 because it doesn't have the knowledge to do that. So it has to come down. That assumption is wrong. The assumption is that the local column does have that
Okay,
information.
hold on. Different question then. Why is the frontal eye field at the top of the hierarchy? I mean, it's like
This I don't understand. So that's a mystery, and we haven't even talked about here at all.
Okay.
Right, so
I think you can think about the frontal eye field as just another type of wear pathway. It's just it just happens to also it has a dominant projection and has an influence on eye saccades, but it's just like other motor pathways. It's not
That's two-hand wavy for me.
No, I mean it's not no different than superior colliculus also drives eye saccades, and those project to V1 as well. So you don't have to have frontal eye fields to do predictive remapping.
yeah.
Right? It's just think of it as another source of motor commands.
Okay, that's
just like
like
any other cortical column outputs motor commands.
Right, but then what about the timing of these signals, right? Because this model makes very concrete predictions about that in part because it has this alpha cycle where you have the prediction sort of running ahead of the feed forward input.
Yeah.
Whereas in a different model you would infer, right, if that wasn't true, right? So if you didn't have a frontal eye field that has a top-down motor plan, right? If this was observed bottom-up, right? Then you would have to recognize
So
that.
let's say, take out the word top down, whatever. All you
Yeah,
need to
yeah.
know is
All you need to know is that there's a
the
motor
motor
command.
command that's being executed. It doesn't
Yeah.
have to be top
And
down.
that
bottom
always
down.
happens before the actual
All
movement.
of our theory says you have to know is what is the motor command that's being executed.
Exactly. That's coming from lots of places.
So it doesn't have to
Right.
be top down. It just needs to be where is my eye moving, how far?
Right.
And then that's
Right, okay.
And remapping signals are seen in V1 and V2 as well.
Right, but what is the temporal latency of that, right? They don't remap before the higher order brain areas. It's a top-down signal.
I'm not sure that's true. Is that true?
Yeah, I'm pretty sure. They actually make that argument explicitly. They even compare to biological time traces.
It depends on.
So you can show, for example, that the LIP remaps before V2. Let me see.
That could be too.
And interestingly enough, not in V1.
All right, so let's just take this up a step, a higher level again.
Mhm.
So I think there are things here which we haven't really dealt with. We haven't dealt with this
Oh,
alpha cycle.
Definitely.
We haven't dealt with really the specifics of the frontal high fields and what the details about them.
Attention.
So what I'm going to stick with for the moment is I'm absolutely certain that this whole concept of locations infused through the cortex, so we have that. The question is, can we merge it with these other ideas?
Exactly.
So, but the other ideas are not that I need to have this hierarchy and propagating back down to do this, because again, all you have to do is even look at the, I always use this example, but it's a very poignant one. The mouse V1 is basically all the mouse has to see, and the mouse sees pretty okay. It doesn't have a hierarchy of stuff, so, you don't have to have this hierarchy. And so somehow we know that, it's just so copacetic of everything. So I'm going to stick with the idea we've got these location signals in every region. And now the question is, well, we haven't really thought about alpha cycles. What's going on there?
Yeah.
We've thought a lot about attention, but we don't have a full model of that.
Well, I think tension can be built on top of this thalamic mechanism, right?
It's the exact same mechanism. That's one of the cool things about this
Everybody believes that attention is part of the thalamus, and we've done a lot of work on that. We've talked about how Supertide worked with the woman at MIT, about how the thalamus could remap these things and what's going on there. So, and that's the idea that thalamus is involved in attentional mechanisms has been around forever. So
And the authors of this paper plan on writing another paper about that, apparently. That's what they left with.
I mean, we looked at in detail about the physiology and the anatomy of the thalamus, trying to understand how these mechanisms work, and the more we can just discover that, better, I guess. The idea that I'm not sure, we don't have the concept of that the input to layer 4 is alternating between a prediction and an actual input. I'm not sure there's evidence for that. Did they give evidence for that? The driver to layer 4 is alternating between predictions and
Yes, there is, because there's this handshake mechanism. So they talk about in the context of what they refer to as like this shielding, right, of the lower layers, so that they can do the prediction as opposed to update from the feed-forward input, which are not supposed
I'm
to
saying
do
when
yet.
you measure, when you look at when you either measure the activity in layer thalamic relay cells, or you measure the activity in layer 4 stellate cells, do they see these two phases? You say, I don't know what the handshake is. Are they seeing these two different things? There's one moment it looks like, hey, these cells are representing prediction, and the next moment they're representing something else. Is there evidence for that? I've never heard that.
In L4, you mean?
Well, L4
L4 cycling like this.
even in the relay cells, it's one or the other. I mean, it's got to be both, right? We're saying these relay cells here are going to be alternating between prediction and actual, and presumably these cells are going to be firing differently between prediction and actual.
Yes, and that's important.
I know, but I don't know. Is there evidence that? Is there evidence that?
I don't know.
When the people talk about the drivers to layer 4, I've never heard that. Maybe there is evidence. I don't know. I haven't heard that. That's a big thing here. It's saying, no, at
Yes,
some point in time,
I agree.
It's going to be a prediction, and other times
It's
it's
an
not.
explicit temporal divide.
So we're running long. We're already
Okay.
15 minutes. So what to do at this point? There's more to read. I haven't even read this whole paper.
I'm not sure, I'm not sure it's worth it at this point in time, Matt. I mean, if you want to go ahead. I think that if you really wanted to delve into this further, personally, from my point of view, I'd want to understand more about the alpha cycle.
Yeah.
I'd want to understand more about the evidence, if there really is evidence for these two phases of these things. That would be an important piece of detail that we have never thought about.
In cortex, I mean.
This projection between, as I just talked about, the relay cells and the layer 4 cells.
Yeah, because they're saying L6 is basically phasic with the thalamus and the minus phase, and from what I heard,
there's this really idea that the driver to a column is into these. One of the main inputs is into layer 4, right?
Yeah.
And the question they're saying here that's alternating between predictions and actual. I have never heard of anything like that.
Right.
So if that is true, I would definitely want to know that. I would like, wow, that's a big piece of data.
That makes sense.
Yeah, I can't find this quickly.
That's like a big idea.
I didn't find it either. I don't remember reading anything about that. The thing when they talk about shielding, they're mostly talking about here, I thought. But I don't know.
I don't know the word shielding means.
Well, they
Sounds like
say
it's preventing
they say the
something.
deep thalamic network is directly responsible for generating predictions over the pulvinar. It must be phasically shielded from the current state, which is this current
Okay,
state.
so the shielding meaning separated or blocked? I don't know.
That
Well,
for
basically shielded, I think just means it happens at different phases.
Okay, great.
Yeah, it doesn't affect, one phase doesn't affect the
Yeah,
other.
okay, great. So now we should see that in layer 4.
Yeah.
We should see that throughout the cortical column because it's also in their model projecting back to layer. You know, we should see that in layer 4. We should see that in the response property of relay cells in the thalamus.
Okay.
Those, and I'm not aware of that ever occurring.
So that's a good question.
Yeah.
That's a big question.
I mean, the one commonality with our models is motion-based predictions occur in layer 6.
Yeah.
In our case, they're not showing the layer 6 to layer 4 loop.
Yeah.
And that's where, we do our predictions and errors.
Why I liked when I wanted to do this, because I thought we could fit our location ideas into something similar, perhaps,
Yeah,
thalamus-wise.
yeah. Well, what's, for example, we have no idea, we have no concept that prediction to layer 4 is ever that projection to layer 4 is ever a prediction. If that were true, we would have to modify our models to accommodate that.
Yeah.
If that basic idea that alpha is a phasic prediction actual thing, and that was actually being projected to layer 4, we would have to accommodate that.
That's an open question for anybody watching. If this thing is phasic, it should be projecting an alternating prediction versus actual to layer 4, and we want to find evidence of that.
Is there evidence for that?
Yeah.
We
Can I
could-
ask a question? Florian, when you were making the latency arguments,
Mm-hmm.
is there any evidence that the circuits can predict forward more than one cycle so that the latency would be phase delayed?
I don't understand.
In other words, you were talking about the argument that you could make that there are signals coming down from the upper levels, in order to drive the predictions.
Well, or inside one level. I mean,
I can answer this question, Kevin, if you
Right.
want. But those measurements have always been based on saccades.
Okay.
So a monkey is saccading, looking at different things. And during the saccade, the cells that are going to become active when the saccade is finished, and some of those cells, not all of them, but some subset of them, become active in advance. It cannot, it does not predict what it will be after the next saccade or 2 saccades. So it's just it's just like, while I'm moving, I predict what I'm going to sense after moving. But it can't predict multiple steps in advance. It's not like it's not like predicting what you're going to see as you're moving along. As the eye is saccading, nothing's happening actually. The basic vision doesn't occur while the eye is moving. It moves very rapidly. Basically, the system shuts off until it stops.
Right.
So it's just predicting what's going to happen after it stops, and it can't predict what's going to do after that because no one could do that because no one's knowing how the eyes are going to move. So, I mean, it's not like the eye is always moving the same pattern. So the answer is no. You can't predict multiple steps. Not those examples.
Okay, because the reason why I asked that is that predicting a single step ahead allows you to do velocity, but if you need acceleration, you need another step beyond that.
Again, don't think of it as you're predicting a moving thing. Those experiments are always predicting the result of a saltatory singular jump.
Right.
And the only next thing that could be predicted is the next saltatory singular jump, which could be in some other direction. And I don't believe the brain knows what that's going to be.
Okay, so you're only looking at a positional shift, nothing.
The conscious experience is somehow fluid and continuous, but neurobiologists would argue that the reality of our perception is discrete and jumpy.
Right, I was just questioning whether it could do more than one time step
No,
in advance.
the answer is no.
All right.
And of course,
Because a lot of times you don't know until you see when you jump and you look at it, that's when you would decide where to
you don't even
connect.
decide most of the time. We're not even talking about this.
It's just when you mention it as a plan, it kind of, it's
Yeah.
an immediate thing, but I just
Right.
wonder if there was a higher order.
The meaning of a plan here is totally different.
No, it's
than the way we
basically
think.
every movement
Yeah.
occurs, and the cortical region says, "Oh, well, given the current movement, what am I going to see next? Oh, given the current movement, what am I going to see next?"
That would be the simplest explanation. I was just,
Yeah.
because if you did have that, then the arguments based upon latencies would get skewed.
And this thing that Florian just mentioned is a huge part of what we try to resolve with our model, which which is you have the stability of perception. You're looking at this picture here, and you have no idea that your inputs to your brain are rapidly changing, but they are 3 times a second.
Yeah.
Completely new input. So you have to explain that. In our temporal pooler with the location signal explains it. It basically says exactly what that does. It says you're going to have a layer of cells which are stable in their activity, yet even though in one layer of cells in the column, even though the inputs of the column are changing rapidly. So that transition from multiple rapidly changing to stable has to occur within a column. It can't occur. It at least has to occur there. And so that was one of the earlier questions I was asking about, like where does that come from? All right.
All right, I think that's it. I'm going to have to figure out what to do next. I haven't decided.
I'll pick another paper.
Pick another paper.
Do a review of alpha cycles.
Yeah, I could do that actually.
Take the deeply alpha paper.
All right, thanks everybody for watching.
Thank you.